Okay, so today we're going to be looking at volumes of revolution. We're going to look at the disk method, and we're going to look at the washer method. So what these methods kind of deal with is in the disk method, we would say, suppose we have a curve, and maybe we're going to look at the region from some A value up to some B value. And so we're kind of looking at the area under the curve between A and B. And then what we're going to do maybe is rotate that area around the x-axis. So if we rotate it around the x-axis, that will generate a solid. It's a little hard to draw, but it'll basically generate a solid that we'll take this part and we'll kind of rotate it all the way around. And that will map out a three-dimensional figure that uses this right here as the cross-section of it. And if this is laying up on the x-axis, the cross-sections will be circles, and that'll kind of outline the disk method. For washer method, this is if you have a region, and say we're dealing with two different curves again, and we're looking at some region, and the area we want to revolve around the axis, there's kind of a gap there. Because when you revolve something like this about the x-axis, there'll be sort of a gap in the middle where nothing is. Then as you revolve the outer shapes, you'll kind of generate these rings or these donut-looking things. And whereas the disk method, the cross-section is a circle, in the washer method, the cross-sections will be circles with a hole in them. And real quick, I'll launch a program where we kind of show the difference one more time. We're going to write out the disk method real quick here. So we'll say for the disk method, we'll say if f of x is continuous and f of x is greater than or equal to 0 on A to B, so the region we're looking at, then the solid obtained by revolving the graph about the x-axis is, so they give us the volume is pi times the integral from A up to B, and we do the radius of the revolution squared dx, which the radius of the revolution, that will be set, so like each of these disks that we get by revolving the part, the radius there will be set by the height of the function. So that will be pi times the integral of A to B times the function value squared dx. So this is kind of the equation we're going to work with. To give you all a slightly clearer idea of disk versus washer method is if we had, say, a part or we were dealing with a graph, let's say that, let's just say real quick that this is our x-axis, let's say here, and this is our y-axis. And let's say we had some sort of curve. So we have a kind of a function curve like that. And let's say we look at the region. Let's say that this right here is the A value and this up here is the B value. So we're looking at kind of looking at this region right here under the curve. If we went to rotate that, and so we say we want to take this little region here, we want to rotate it about the x-axis. Whoops. Well, maybe we got to clip the rest of the function first before we can rotate it. But if we have that area there, and that's the area we're dealing with, and we want to rotate it about the x-axis, it makes a shape like this. And the cross sections of this sort of shape, these are disks. So these are circles, which they call disks. So a shape like this would be something that's generated using the disk method. If we had the washer method, this would be like, suppose this function we're dealing with, suppose there's a second curve on the underside. So suppose there's like another curve there, and we're talking about revolving the shape. Now instead of the original shape, we're revolving this area where there's kind of a gap there. When we do that, the cross sections on this area, when we go to revolve it, the cross sections on this area now are washers, where they're like circles with a hole through it. So that's kind of the difference between disk method versus washer method. Is disk method whenever the area touches the axis you're revolving around and you revolve it, you get a solid shape that doesn't have a hole through it. Whenever the region you're going to rotate is above the axis by a bit, when you revolve it around, you get kind of these washer shapes as cross sections. So they look kind of like a ring, and they have a hole through it because the where you're revolving it about is above the axis of revolution. So we're going to focus on the disk method first. So we'll deal with types like this, where they're sitting right on the axis we're going to revolve, and then the rest of the chapter will deal with washer method. So for our first example, we're going to say we want to calculate the volume. By rotating the region. So by rotating the region under the graph. And they give us the function y equals x squared about the x-axis for 0 is less than or equal to x is less than or equal to 2. So we want to focus on doing that. So what we're going to do here is we're going to build a graph. We're going to look at our x squared function, which will be just the basic parabola. Since we're only looking at the 0 to 2 side, I'm just going to draw the right-hand side of the parabola. So we start at 0. We're going to stop up here at 2. So this shape here, if I revolve this shape, this is the area we're going to revolve. And if we revolve it, we get basically a little kind of cone shape. If we revolved it, our revolution is going to look kind of like that. Basically, this part here, when we revolve it, will turn into kind of a cylinder, or so turn into a circle. And as we revolve the rest of these, they'll make kind of a little cone shape that comes to a point. So what we do is we say, okay, the height of each of these points, or each of these circles that we're going to generate, the height of the function at that particular point will be the radius of the circle that's generated. So we're going to say, all right, the volume will equal, it'll be pi, we're integrating from 0 up to 2, and it's going to be the radius squared, which is basically just the function. So we say, all right, that's going to be x squared, our function, because that sets the height of each of these individual points, will be the y value given by the function. We square it, and then we get dx. So basically what we're doing here is using this equation. Our function's x squared in this particular point. We're integrating from 0 up to 2. And then all we have to do is just calculate it out. So this will be pi integral from 0 to 2 of x to the 4th dx. That will be pi times 1/5 x to the 5th integral of 0 to 2. So we could say this will be pi x to the 5th over 5 evaluated from 0 to 2. So we use fundamental theorem of calculus part 1. That'll be pi times 2 to the 5th over 5 minus pi times 0 to the 5th over 5. 0 to the 5th over 5 is just 0, so that term goes away to 0. 2 to the 5th is 32, so we have 32 pi over 5 for our answer to that one. That will be the volume. They didn't give us units, so it's cubic units, but they didn't tell us what the units are. So we'll just leave it as a blank. If you wanted to, you could say it's that many units cubed. So that was the one example of a DISC method the book gave us. We're going to look at the rest of this time. The DISC method's not too bad because you just kind of load the function in and integrate it over the region. The rest of the examples are going to be washer method, which washer method's a little bit trickier. You have the volume of the washer method. It's going to look similar to the DISC method, but since we have kind of in the washer method, we have when you do this, you have kind of a outer radius that's set by one of the function values that sweeps the outer circle, and you have an inner radius that's set by the second function that'll act as the radius for the inside circle. We have to kind of account for both of those, and in the equation, the way it looks is we get r, we'll use subscript outer. So it's the outer radius squared minus the inner radius squared dx. And this will equal, if the outer radius was a function f of x, this would equal the outer function's y value minus the inner function's y value. And you'd integrate that with respect to x. So this is going to be the washer method. And you deal with these integrals when you're kind of generating shapes like this where there's like a hole through it. And the outer radius of this expression would be given by the distance from here up to the outer line, and the inner radius would be from the point up to the closer line, because when you sweep this around, the outer line generates the outer edge of the shape and the inner line generates the inner edge. And then the integration, you would start at one point, stop at the other. You'd be just basically stacking these washer shapes up on each other to make the three-dimensional shape. So let's look at an example or two. First example here. We want to find the volume of revolving the region between, they give us the function y equals x squared plus 4 and y equals 2. About the x-axis, for the x's from 1 up to 3. So we'll take a look at that. So we're basically only looking at x's from 1 up to 3. We're looking at x squared plus 4. X squared plus 4 has a y value. It's the basic parabola shifted up 4. So we're going to just kind of draw the positive side of the parabola shifted up 4. Try to do a little better job, something like that. Since we're only looking at the region 1 to 3, we're only really interested in what's going on here from 1 up to 3. We're looking at that region and the line y equals 2. So the line y equals 2 is the horizontal line here. So if we kind of look, we're looking at this region from 1 up to 3. So the area we're going to revolve is going to look something like this, where the outer radius is given by the function x squared plus 4, and the inner radius is given by the line y equals 2. So if we revolve it, it'll make a similar shape to that one we were kind of talking about a little bit. You'll have the outer radius, you'll have the inner radius, and down here you'll have the inner radius, and you'll have your outer radius, and you'll be basically generating a volume like that. If we wanted to see a little bit of an example, just kind of what it really would look like, we could say, let's try to, let's see here. Let me get rid of this right here, and we'll just try to draw as best we can a parabola. So we'd say, all right, from here, we want to draw a parabola shape. So we'd say here's maybe 4. And so we'll start drawing our parabola curve kind of up something like that. We draw the line y equals 2 in there. We're only interested from x equals 1. So we'll say x equals 1 is here, up to x equals 3, which we would say is possibly there. And let's clip this up. So this is kind of the shape that we have that we want to revolve. We can see here it's kind of a similar looking shape to what we have there. And then we're going to revolve it around this x-axis. So that'll generate a three-dimensional shape that looks kind of like this that we're trying to find the volume of. And we can see in this shape here, we can kind of see the we're using the washer method because there's this gap through the middle, so each of the cross sections, instead of just being a circle, they're now kind of like a washer. So that's what this revolution is going to look like. What the equation says we're going to do is we're going to do the integral from a up to b, the pi out front. It's going to be the r outer radius squared minus the r inner radius squared dx. So for this particular problem, the outer radius, the y value of the outer radius, if you start here, that's given to you by the equation x squared plus 4. So this will equal pi. We'll get our limits of integration in a second. The outer radius will be the x squared plus 4 function. So we have the outer radius squared. The inner radius is this, given by this y equals 2. So that'll be minus the inner radius squared, which would be minus 2 squared. And for our limits, we're integrating from x equals 1 up to x equals 3. So we'll put a 1 up to 3 there. And now when I go to integrate this, I'm going to actually FOIL out this first term to make it easier to take the antiderivative of it. So we're going to get, if we FOIL it out, we're going to get x to the 4th. We'll get plus 8x squared plus 16. We'll have minus 2 squared is minus 4 dx. So that will be pi integral of 1 up to 3 of x to the 4th plus 8x squared plus, that would be 12. So we want to integrate this from 1 up to 3. So when we integrate that from 1 up to 3, x to the 4th will integrate and it'll become 1/5 x to the 5th. Plus x squared will turn into an x cubed. It'll turn into a 1/3 x cubed. So we'll have an 8/3 x cubed. The 12 will turn into just a 12x. We'll integrate it from 1 up to 3. And so we'll get this expression here with 3 plugged in first. So we're using Fundamental Theorem of Calculus Part 1 here. We get this all with 3's plugged in, and then we get this all with just 1's plugged in. So I'm taking the same equation and I'm replacing the x's with 1's. Okay, and when we solve this all out, if we either put it in the calculator or do this out by hand, this eventually will all turn into 2126 over 15 times a pi. So in interest of time, we won't solve that out by hand, but you could either do it by hand or by a calculator. It will eventually turn into this. We don't have units on this again, so we could say it's units cubed for cubic units if we wanted to. If they told us this was like meters or centimeters, we'd be able to be more explicit and write out if it was cubic meters or cubic centimeters or whatever. Okay, so next couple problems we got here. For this example, we want to find the volume of revolving the area between, got two functions, f of x equals x squared plus 2, and g of x equals 4 minus x squared, about the horizontal line, y equals -3. Okay, so first let's kind of get an idea of what we're doing here. So here's our x-axis. Here's our y-axis. We got x squared plus 2. Oops, I guess I should center these better because we're dealing with both sides in this case. We got x squared plus 2. That's going to be the basic parabola shifted up 2 units. So that'll look like this sort of. We have 4 minus x squared. So that'll be 4 minus x squared will be the parabola that opens downwards like that. So the area in between these two shapes is this region right in here. And instead of revolving these about the x-axis, we're supposed to go down an extra 3 units and revolve these about the line y equals -3. So this is going to make kind of a ring shape, but it's when you revolve it, it's going to be it'll look kind of like that. It's actually kind of a hard picture to tell what's going on. Let's see if we can kind of sketch what the shape's going to look like in here. So let's see. To give you all some idea of what it might look like. So say, let's see, extend our line here. So here's sort of our x-axis and our y-axis. So we have kind of 2 parabola shapes. I'm going to sketch them. They won't be perfect, but we have kind of the parabola shape that is up 2, and then it goes a little bit higher up to the right like that. We have a second parabola that starts here at 4 and kind of heads downwards like this. Let me get those shapes on the other side as well. And so when we have this, if we kind of look at the area we're dealing with a little shape kind of like that. So we have kind of that similar shape to what we're seeing here. It's kind of the region in between these two. And then instead of revolving this about the x-axis, we're supposed to go down another 3 units. And we're supposed to revolve it about this line down here. So we'll revolve that shape, and we're going to revolve it way down there. And that'll make a shape kind of like this. We revolve it around this bottom line, and the result we get is kind of a some sort of like ring-looking shape. So that's the visually that's what we're trying to do. Mathematically, what we need to find, we're going to be using the same formula we were using a minute ago. We're going to be using pi times integral from a to b of outer radius squared minus inner radius squared dx. So the outer radius for this right here will be the function that points downwards. So the outer, because over the region, which we'll need to figure out where are we integrating from and to, we'll need to figure out those intersection points in a little bit. The outer radius is the downwards parabola, which the downwards parabola is the 4 minus x squared. And the inner radius will be this parabola that's closer to the line, which is the parabola that opens upwards, which is x squared plus 2. That will be our inner parabola, or our inner radius. So we get the integral of, we'll have to figure our limits in a minute. Our outer is 4 minus x squared squared, minus our inner is x squared plus 2. Whoops, I just made a mistake. So that gets us the distance. This gets me the distance to, the outer will get me the distance down here to the y-axis. I need to add an additional 3 to get it down to the line y equals -3 that we're actually going to revolve it around. So what I'm actually dealing with here is 4 minus x squared. That's the g of x function. And I have to add an additional 3 to it to get the radius to be all the way down here at y equals -3. And for the inner function, I have to do the same thing. If I'm on the inner line, the x squared plus 2 only gets me back to the x-axis. Since we're revolving it 3 units lower than the x-axis, I need the radius down to that lower point. So I need to add 3 to this as well to generate the full radius of where we're going to revolve around. So we're going to say this will be minus the r inner, which was x squared plus 2. And we have to add an additional 3 to it as well to make the make what's eventually going to be spun around That'll make those radiuses the correct height. So when you're going about the x-axis, you just use the functions themselves. If you're going about a different line, like in this case we have an extra 3 units below the x-axis, you need to account for that when you figure out your radiuses. To figure out my limits now, I'm going to say where is x squared plus 2 equal to 4 minus x squared? Where does that happen? So I'll add my x squareds across. I'll subtract my 2 across. I'll get 2x squared equals 2, which will say x squared is 1, which will say x is plus minus 1. So this here occurs at x equals negative 1. That one stops at x equals positive 1. So we're going to be integrating this from negative 1 up to positive 1. Okay, so first let's algebraically clean up our stuff, and then we'll FOIL it out. So here we got 4 plus 3 is 7 minus x squared minus x squared plus 5 squared dx. So in order to do this, I'm going to FOIL the first bit here. So 7 times 7 is 49. We have minus 7x squared from the outer, minus 7x squared from the inner, so that'll be minus 14x squareds. The negative x squared times another negative x squared is positive x to the 4th. So that's what we get from FOILing out this first chunk. And then we're going to subtract from it what we get when we FOIL out this bit here, which will be 4x squared plus 10x plus 25. Okay. So let me distribute the negative, and we'll do some of that addition and subtraction in our head to generate the final form of what we're actually going to go through and integrate. So I have positive x to the 4th and negative x to the 4th. So that actually cancels out all the x to the 4ths. I have negative 14x squareds. The negative distributes, so I get minus another 10x squareds, which would be negative 24x squareds. I have 49 minus 25. If we have 49 and we take 25 away from it, that leaves me a 24, and it's going to be positive. Okay. So here we're ready to take our antiderivative. We have pi. X squared will integrate and become 1/3 x cubed. 1/3 of 24 is 8, so we get negative 8x cubed. Plus the 24, we just put an x after it. And that's going to be integrated from negative 1 up to 1. So I use Fundamental Theorem of Calculus Part 1. This will be pi times negative 8 times 1 cubed plus 24 times 1 minus pi times negative 8 times negative 1 cubed plus 24 times negative 1. Okay, so let's see here. This is going to be just negative 8. That will just be 24. 24 take away 8 is 16, so we have 16 pi here. And then we're going to subtract from it. Let's see, negative 1 cubed is negative 1. Negative 1 times negative 8 is positive 8. This will be minus 24. That'll be negative 16 times pi, so that'll be minus 16 pi. So I have 16 pi minus a negative 16 pi. Minus a negative is plus. So 16 pi plus 16 pi is plus 32 pi. So that would be the volume that you get from revolving this shape here. That would be the volume that this sort of ring shape that we get from revolving that has. Okay. So next one that we look at is going to have kind of two parts. Got a part A and a part B. So they want us to find volume of rotating graph, the area between graphs. They give us f of x equals 9 minus x squared and y equals 12 over from 0 up to 3. Part A is about, they give us the line y equals 12. Part B, they give us about the line y equals 15. So let's graph these to get an idea of what we're dealing with here. See, we're only doing 0 to 3, so from 0, 1, 2, 3. 9 minus x squared will go 2, 3, 4, 5, 6, 7, 8, 9. It'll be a parabola that has a y-intercept of 9, and it will come down and have an x-intercept of 3. The line y equals 12. Let's see, we're at 9, 10, 11, 12. That'll just be a straight line across like that. So the region we're dealing with is this sort of shape right here. Well, if we want to revolve it about the line y equals 12 like we do in part A, since this line here is at 12, that's going to generate a revolution where we just have a bunch of circles with no gap in the center. So we're going to use this method to get that. We just need to see, well, what would become the radius of that expression will be a line from here up to here. So this will be the radius when the thing gets revolved. So that expression there, if we want to say what the length of that is, that would be the upper value 12 minus the function curve down here, which would be, what did we say that was? 9 minus x squared. That will give me the distance between these two curves. So when I go to do the integral, I want the integral, we're dealing with 0 to 3. This would be pi times that radius, which would be 12 minus 9 minus x squared dx. And then we'll just have to calculate that out. So we're going to have to do, let's see here, what do we get? Let the negative distribute. So minus a negative x squared is a positive x squared. And then 12 take away 9 would be 3. So we get x squared plus 3 squared dx. So I'm going to have to FOIL that out to get the volume. When we FOIL it out, we'll get x to the 4th plus 6x squared plus 9 dx. Okay. When we integrate this, this will be pi times x to the 4th goes to 1/5 x to the 5th. And x squared will go to 1/3 x cubed, and 1/3 of 6 is 2, so that'll be plus 2x cubed. And then 9 goes to just plus 9x. We get that evaluated from 0 up to 3. So we're going to substitute 3 in. So we get 3 to the 5th. Plus 2 times 3 cubed plus 9 times 3 minus what we get when we substitute 0 in. Let me say it this way. So I'm just going to write this kind of vertically because we have the part B. I wanted to leave some room to do part B over there. So we have that plus, let's see, it would be 2 times 0 cubed plus 9 times 0. This whole term here goes to 0 because all of these have at least one 0 multiplied in them. And if we do the top part, if we work that all the way out, and we end up with, we'll end up with 648 over 5 times pi. So if we were to solve all of this stuff here out, type it in a calculator, just do it out by hand, that will turn into this. Okay, for the part B, what if we, instead of revolving along the line y equals 12, what if we revolve around a line a little bit higher, 13, 14, 15, so we have a line up here at y equals 15 that we want to revolve. Now there is a outer radius, which will be from here up to here, and there'll be an inner radius, which the inner radius will be from there up to there. So So the inner radius, the spacing between 12 and 5, the inner radius is going to be 3 because 12 and 5 are spaced by 3 units. For the outer radius, we're going to get, it's going to be this 9 minus x squared. It'll be that function plus the additional 3 units. Oh, wait, no, sorry, just kidding. 9 minus x squared is the distance from here down to here. We need the distance between these two, so that'll be 12 minus 9 minus x squared. That's the distance from here up to here, the distance between the 12 and that, and then we need to add an additional 3 to that. Okay, so let's write out the integral over here. It'll be pi times integral 0 to 3. The outer radius will be this one. I'm going to do 12 plus 3 is 15, so that'll be 15 minus 9 minus x squared whole bit squared minus the inner radius, which the inner radius will be 3, so that'll be minus 3 squared. This will be dx, so we're still integrating with respect to x, because we're going from 0 up to 3 along the x's. So let's algebraically start simplifying stuff. We get pi integral from 0 to 3. 15 minus 9 is 6, so this will be 6 minus x squared minus 9 dx. If we FOIL it out, we'll get the integral from 0 to 3. That'll be 36 minus 12x squared plus x to the 4th minus 9 dx. This will equal pi integral of 0 to 3. 36 take away 9 should be 27. So this will be 27 minus 12x squared plus x to the 4th dx. We'll take the antiderivative here. This will go, 27 goes to 27x. 12x squared, the x squared goes to 1/3 x cubed. 1/3 of 12 is 4, so this will be minus 4x cubed. And x to the 4th will go to 1/5 x to the 5th. Integrate from 0 to 3. So what we'll get is we'll plug, get all this stuff with 3 substituted in. And then we'll subtract from it all of this stuff with zeros plugged in. Which, if you look at that, the way the zeros fall, the second term here is all going to be 0. And if we total this up right here, if we figure out what is just this part here, if I type that in a calculator, work it out by hand, that ends up being 1188 over 5 times pi. So that is our 4th example. This one used the washer method. Our final example here is going to be the last one from the section. We're going to look at this example here, which says we want to find the volume. So find volume from revolving the region under the graph of 9 minus x squared for 0 is less than or equal to x less than or equal to 3. About axis x equals -2, which is a vertical axis. So basically, this time what they're asking us to do, 9 minus x squared is a parabola. We're up here at 9. It has a x-intercept down here at 3. So we're looking at kind of this part of the curve of a parabola. And they're telling us to take that part. Here is the line x equals -2. And they want us to revolve this shape here about that line. So real quick, just to kind of draw a visual of what that would look like so we can kind of get a better idea. Get rid of the last stuff we were looking at here. So we have a parabola shape that's basically kind of looks like this sort of thing. We're going to kind of put some lines on it so we can get the region that we're talking about. So we're talking about a region like that. And this time we're going to be revolving that about x equals -2. If x equals -1 was there and x equals -2 would be a line like that. We're going to revolve this about a line like this. And this will be kind of the volume. This will be the shape that we're trying to figure out. So we can see we're going to have to use a washer method because there's a hole through the center of it. But it's basically half a parabola that's been revolved around some line that's a little bit beyond the axis. So what we're going to be doing with this, our outer will be from that line over to here. Our inner will be from this line here over to the inner edge. Our inner is just going to be a number. It's going to be, since we're doing this at -2, that will just be 2 units. So our inner is just 2 units. Our outer, I have to take this expression, the graph that they gave us, y equals 9 minus x squared, and I need to solve it for x since I'm integrating with respect to y this time because we're going to be stacking the disks on top of each other. So our integral is going to run from 0 up to 9. We'll get, let's see here, that'll be positive x squared equals 9 minus y. So x will equal plus or minus square root of 9 minus y. So positive square root of 9 minus y. That'll get us the distance from the curve to the axis here. We have to add an additional 2 to it to get that distance from the this back to there. So we got our outer and our inner. We're going to say pi integral from 0 up to 9. It'll be the outer radius squared, which will be the square root of 9 minus y plus 2. That's our outer radius squared. Minus the inner radius squared, which would just be 2 squared dy this time. So in order to calculate this, let's see here, we have pi integral of 0 to 9. I'm going to FOIL this out. Square root of 9 minus y times another square root of 9 minus y would be square root of 9 minus y squared. That'll just be a 9 minus y. The outer term would be plus 2 square roots of 9 minus y. The inner term would be plus another 2 square roots of 9 minus y. So we get 4 square roots of 9 minus y. And then we'll get 2 times 2, which is plus 4. And then we'll have minus the 4 over here. Plus 4 minus 4 will cancel. We go to integrate this. I'm going to split the integral up because the second part of the integral, I'm going to need to use a u substitution on it. I'm going to push the 4 out front also. So I'll push the 4 out front of the integral. Okay, so when we integrate this part, we get pi times, it'd be the antiderivative of 9, which would be 9y, minus y itself will go to 1/2 y squared. You'll evaluate that from 0 up to 9. Plus, for this one here, we're going to use u equals 9 minus y. Then du would be negative dy. We have the dy. I'm going to make this negative, which means I have to put a negative out front there. So we will have negative 4 pi integral of, if I put 0 in for y, 9 minus 0 is 0. If I put 9 in for y, 9 minus 9 is, oops, hang on a second, I did that backwards. If I put 0 in, 9 minus 0 is 9. If I put 9 in, 9 minus 9 is 0. This will be square root of u is 9 minus y. And then negative dy is du. So we can calculate that antiderivative that way. This will be pi times 9 times 9 minus 1/2 times 9 squared minus, let's see here, we'll put 0 in, pi times 9 times 0 minus 1/2 0 squared, which that term actually is just 0, plus we'll integrate this. This will be, let's see here, u to the 1/2 goes to u to the 3/2, so we'll have a 2/3 out front. 4 pi times 2/3, that will be negative 8 pi over 3. And then we'll have u to the positive 3/2. And then we'll be integrating that from 9 up to 0. So let's see here. This is 81. This is 81 halves. If I have 81 and I take away 81 halves, I have 81 halves left. So I have 81 pi over 2 from the first bit. And now we're going to add to it what we get when we substitute stuff in here. We have negative 8 pi over 3 times 0 to the 3/2. And then we're going to have minus a negative 8 pi over 3 times 9 to the 3/2. This term here is just 0. Minus a negative is plus. Let's see here. This says take the square root of 9, which is 2, then cube it. 9 cubed is 3 cubed is 27. We get 27 divided by 3 goes back to 9. 9 times 8 pi is 72 pi. So I have 81 pi over 2 plus 72 pi. I need to get that in terms of halves. So that's 81 pi over 2 plus 144 pi over 2, which is, let's see here, 1 plus 4 is 5. 8 plus 4 is 12. Carry the 1, so it's 225 pi over 2 for our volume in this situation. And that basically wraps the section up. So this is where you revolve this method or you revolve using washer method. So we'll stop there.